Imagine standing outside on a perfectly clear night, far from the glow of any city, somewhere in a desert or on a mountaintop where the air is thin and still. You look up, and what you see is not just a sky full of stars. What you see is a cathedral of light stretching from one horizon to the other, a river of luminous dust that our ancestors called the Milky Way. Each point of light you see is a sun. Many of those suns are larger than ours. Many of them are older than ours, some by billions of years. And around those suns, as we now know with scientific certainty, orbit planets. Billions upon billions of planets. Rocky planets, watery planets, planets with thick atmospheres and planets with thin ones. Planets sitting in the habitable zones of their stars, where temperatures allow liquid water to exist on the surface. And liquid water, as far as we understand it, is one of the most fundamental prerequisites for life as we know it. So when you stand there, looking up at that sky, you are not just looking at pretty lights. You are looking at the most profound question humanity has ever confronted. If the universe is this old, this vast, this filled with the raw ingredients of life, then where is everybody? Why is it so silent? Why, in all our decades of searching, in all our centuries of watching the skies, have we found absolutely nothing? No signals, no visitors, no ancient artifacts drifting between the stars, no megastructures dimming distant suns, nothing, just silence. A silence so deep, so total, so persistent, that it has earned its own name among scientists. They call it the Great Silence. And for more than 70 years, that silence has haunted every physicist, every astronomer, every biologist, and every philosopher who has dared to take it seriously. But what if the silence itself is the answer? What if the reason we hear nothing is not because no one is out there, but because everyone out there has learned, perhaps through bitter experience, perhaps through cold logic, that making a sound is the most dangerous thing a civilization can do? What if the universe is not empty but full, and the reason it appears empty is that every intelligent species in it is hiding not from us, but from each other, hiding because they have all arrived at the same terrifying conclusion, a conclusion so dark, so logical, so inescapable that once you understand it, you will never look at the night sky the same way again. This is the dark forest theory, and today we are going to explore it from every possible angle, from the first moment the question was asked to the cutting edge of modern science and game theory. We are going to trace the history of humanity's search for extraterrestrial intelligence, examine every signal we have sent, and every silence we have received in return. We are going to walk through the logic step by step, axiom by axiom, until we arrive at a conclusion that might genuinely change how you think about our place in the cosmos. Everything you are about to hear is grounded in real science, real history, real mathematics, and real philosophical debate. No speculation, no fantasy, no what-if scenarios. Just the facts, the logic, and the silence. Before we enter the dark forest, I want to ask you something. Think about it honestly. Do you believe we are alone in the universe? And if we are not alone, why do you think no one has made contact? Hold that thought, because by the end of this, your answer might be very different from what it is right now. And if you are the kind of person who lies awake at night thinking about these questions, the kind of person who looks up at the stars and feels that mixture of wonder and unease, then do me a favor. Hit that subscribe button right now, like this video, and drop a comment telling me what you think the answer is. Because this journey we're about to take together is one of the most important intellectual voyages you will ever go on. And I want to take it with people who genuinely care about the truth. Now, let us begin at the beginning. Let us go back to a summer day in 1950, to a place called Los Alamos, in the high desert of New Mexico. Los Alamos National Laboratory in 1950 was one of the most intellectually concentrated places on the planet. It was where the atomic bomb had been built. It was where some of the greatest scientific minds of the 20th century gathered to push the boundaries of physics. And on this particular day, 4 of those minds were walking together to lunch at a building called Fuller Lodge. Their names were Enrico Fermi, Edward Teller, Emil Konopinski, and Herbert York. Fermi was an Italian-born physicist who had won the Nobel Prize in 1938 for his work on nuclear reactions. He had predicted the existence of the neutrino, a particle so ghostly that trillions of them pass through your body every second without interacting with a single atom. He had built the first artificial nuclear reactor, Chicago Pile 1, in a squash court beneath the University of Chicago Stadium in 1942. He was legendary not just for his brilliance, but for his ability to estimate almost anything with startling accuracy, using what came to be known as Fermi questions, simple-seeming puzzles that required deep reasoning to solve. How many piano tuners are there in Chicago? How many atoms of Caesar's last breath do you inhale with each breath you take? These were the kinds of questions Fermi loved. As the four physicists walked to lunch that day, their conversation was light. They were talking about recent newspaper reports of flying saucers, which had become something of a cultural phenomenon in America. There were jokes about faster-than-light travel and its feasibility. They laughed. The conversation moved on to other topics. And then, as they sat down at the table in Fuller Lodge, Fermi suddenly said something that stopped the conversation dead. The exact words have been recalled differently by each of the men who were there. Edward Teller remembered it as, "Where is everybody?" Herbert York recalled, "Don't you ever wonder where everybody is?" Emil Konopinski's version was, "But where is everybody?" The phrasing varied, but everyone at the table understood immediately what Fermi meant. He was not asking about their colleagues, he was asking about extraterrestrial civilizations. And according to Teller, the result of Fermi's question was general laughter, not because it was funny, but because of the strange fact that despite the question coming completely out of the blue, everybody at the table immediately understood that he was talking about extraterrestrial life. According to Herbert York, Fermi then followed up with a rapid series of calculations. He estimated the probability of Earth-like planets existing. He estimated the probability of life arising on those planets. He estimated the probability of intelligent life developing. He estimated how quickly a technological civilization might develop interstellar travel. And he concluded, based on these calculations, that Earth ought to have been visited long ago and many times over. The galaxy is roughly 13.6 billion years old. Our solar system is only 4.6 billion years old. That means there were star systems forming, planets cooling, and potentially life evolving for 9 billion years before Earth even existed. 9 billion years is an almost incomprehensible amount of time. Even if interstellar travel is slow, even if it takes millions of years to cross the galaxy, that is still just a fraction of the time that was available. Some civilization somewhere should have had enough time to expand across the entire Milky Way, and yet there was no evidence of this whatsoever. No visits, no artifacts, no signals, nothing. This was the birth of what we now call the Fermi Paradox. And it was not just a casual question. It was, and remains, one of the most profound unsolved problems in science. Now, it is important to understand that Fermi was not actually the first person to notice this contradiction. In 1686, a French writer named Bernard Le Bovier de Fontenelle published a book called Conversations on the Plurality of Worlds, in which he discussed the possibility of intelligent beings on other planets. In that book, a character challenges the idea by pointing out that if intelligent life existed on the moon, its inhabitants would have come to visit us by now. This is essentially the same argument Fermi made 264 years later. Jules Verne touched on a similar idea in his 1865 novel, Around the Moon. And in the 1930s, a Russian rocket scientist named Konstantin Tsiolkovsky explicitly laid out the paradox, noting that if advanced extraterrestrial civilizations existed, they should have visited Earth or left detectable evidence. Tsiolkovsky even proposed a solution. Perhaps aliens are deliberately quarantining us to allow our culture to develop independently, an idea remarkably similar to what would later be called the zoo hypothesis. But Tsiolkovsky's philosophical writings were suppressed by the Soviet government, and his ideas remained largely unknown to the Western scientific community for decades. It was Fermi's casual lunchtime remark that captured the scientific imagination and gave the paradox its name. The term Fermi Paradox was first coined in a 1977 article. Though the concept had been discussed in scientific literature since the 1960s, first appearing in print in a 1963 paper by Carl Sagan. In 1975, Michael Hart published a detailed analysis in the Quarterly Journal of the Royal Astronomical Society, proposing 4 broad categories of solutions: physical constraints on space travel, sociological reasons why aliens might choose not to visit, temporal explanations suggesting aliens have not had enough time, and the possibility that aliens have already visited without our knowledge. Hart's paper triggered an explosion of academic interest, even reaching the British House of Lords, where the topic was formally discussed. Frank Tipler followed with an influential paper, arguing that if advanced extraterrestrial civilizations existed, their self-replicating probes should have already been detected in our solar system. And since they had not, such civilizations likely did not exist. The political ramifications were real. The popularization of the Fermi Paradox actually damaged the search for extraterrestrial intelligence. In 1981, US Senator William Proxmire cited Tipler's arguments when he successfully pushed to terminate NASA's federally funded SETI program. The search for alien life was politically radioactive for years afterward, and it took the rise of private funding to restart the effort. But the paradox itself only grew more urgent with time, because the numbers kept getting more extreme. Let us talk about those numbers, because they are genuinely staggering. The Milky Way galaxy alone contains between 200 billion and 400 billion stars. That is, 200,000 million to 400,000 million stars in a single galaxy. Our galaxy is just one of approximately 2 trillion galaxies in the observable universe. That means the total number of stars in the observable universe is somewhere around 70 sextillion, which is written as a 7 followed by 22 zeros. To put that in perspective, there are more stars in the observable universe than there are grains of sand on every beach on Earth. Every single one of those stars is a potential sun, a potential host for planets, a potential home for life. And we now know, thanks to missions like NASA's Kepler Space Telescope and the Transiting Exoplanet Survey satellite, that planets are not rare, they are incredibly common. On average, every star in the Milky Way has at least one planet. Many have several. The Kepler mission alone confirmed the existence of over 2,600 exoplanets and identified thousands more candidates. Based on this data, astronomers estimate that there are at least 100 billion planets in the Milky Way. Of these, billions are in the habitable zones of their stars, meaning they orbit at distances where liquid water could exist on the surface. Some estimates suggest there could be as many as 40 billion Earth-sized planets in habitable zones in the Milky Way alone. Many of these star systems are much older than ours. The Sun is about 4.6 billion years old, but many Sun-like stars in the Milky Way are 8, 9, even 10 billion years old. That means, if life arose on planets around those older stars at the same rate it arose on Earth, there could be civilizations out there that had a 5 billion year head start on us. 5 billion years. Think about what humanity has achieved in just the last 10,000 years, since the agricultural revolution. Now imagine what a civilization could achieve with a 5 billion year head start. The technologies such a civilization would possess would be to us indistinguishable from magic. They could have colonized not just their own solar system, but the entire galaxy, and had billions of years to spare. In 1961, astronomer Frank Drake attempted to formalize the question by developing what became known as the Drake equation. He presented it at the first scientific meeting on the search for extraterrestrial intelligence, held at the Green Bank Observatory in West Virginia. The meeting had just 10 attendees, including Drake himself and Carl Sagan. The equation estimates the number of active, communicative extraterrestrial civilizations in the Milky Way by multiplying together a series of factors: the rate of star formation in the galaxy, the fraction of those stars that have planets, the number of planets per star that could potentially support life, the fraction of those planets where life actually develops, the fraction of those life-bearing planets where intelligent life evolves, the fraction of those intelligent civilizations that develop technology capable of producing detectable signals, and the length of time such civilizations release those signals into space. The equation looks elegant and scientific, but here is the problem. We only know the first couple of terms with any confidence. The rate of star formation is roughly 1.5 to 3 new stars per year. The fraction of stars with planets, as we now know, is very high. But after that, every single term is essentially a guess. We have no idea how likely it is for life to arise from non-living matter. We have exactly one example: Earth. We do not know if the origin of life was easy and inevitable given the right conditions, or if it was a freak cosmic accident that happened once in the history of the galaxy. We have no idea how likely it is for intelligent life to evolve once simple life exists. On Earth, it took roughly 4 billion years to go from single-celled organisms to human beings. Is that typical? Is it fast? Is it slow? We do not know. We have no idea how likely it is for intelligent life to develop detectable technology, or how long such civilizations typically last before they destroy themselves or go silent. The participants at that first SETI meeting, using optimistic estimates, calculated that there might be between 1,000 and 100 million communicative civilizations in the Milky Way alone. Using pessimistic estimates, Frank Tipler and John Barrow later calculated that the average number of civilizations per galaxy might be much less than one. A 2018 analysis by Anders Sandberg, Eric Drexler, and Toby Ord at the Future of Humanity Institute at Oxford took a different approach. Instead of guessing specific values for the unknown terms, they analyzed the full range of scientific uncertainty for each parameter. Their conclusion was striking. Given our current state of ignorance, there is a substantial probability that we are alone in the observable universe. Not because life is definitely rare, but because our uncertainty is so vast that being alone is one of the plausible outcomes. But here is the thing. Even the pessimists acknowledge that the odds should favor life being out there. The universe is simply too large, too old, and too full of the building blocks of life for it to seem reasonable that we are the only ones. And yet, the evidence says we are. This is the paradox, and it has driven scientists to propose dozens of solutions, each more creative, more unsettling, or more bizarre than the last. Before we get to the dark forest theory itself, we need to understand what humanity has actually done to search for extraterrestrial intelligence, because the depth of our search makes the silence even more profound. The modern search for extraterrestrial intelligence began in 1960, when Frank Drake pointed an 85-foot radio telescope at the Green Bank Observatory in West Virginia at two nearby sun-like stars, Tau Ceti and Epsilon Eridani. He called it Project Ozma, named after the Queen of the Land of Oz, a place very far away, difficult to reach, and populated by strange and exotic beings. Drake listened for several months, scanning the radio frequency at 1420 MHz, which is the frequency at which hydrogen, the most abundant element in the universe, naturally emits radiation. Scientists reasoned that any intelligent civilization trying to communicate would likely choose this frequency because it is a universal constant, a natural meeting point on the electromagnetic spectrum. Drake found nothing, but the search had begun. Through the 1960s and 1970s, SETI efforts expanded. Multiple observatories around the world joined the search. Ohio State University's Big Ear Radio Telescope conducted the longest-running SETI survey of that era, scanning the skies systematically for unusual signals. It was the Big Ear that, on August 15, 1977, detected the most famous signal in SETI history. On that evening, the telescope picked up a narrowband radio signal that lasted 72 seconds. The signal was powerful, roughly 30 times stronger than the background noise. It appeared at a frequency very close to the hydrogen line at 1420 MHz, exactly where scientists would expect an intentional extraterrestrial beacon to broadcast. The signal appeared to come from the direction of the constellation Sagittarius, in a region of sky with no known bright stars or obvious natural sources. When astronomer Jerry Amon reviewed the computer printout the next day, the data sequence read 6EQ-UJ5, representing a sharp spike in signal intensity. Amon was so astonished that he circled the sequence with a red pen and wrote a single word in the margin, "Wow." The wow signal, as it became known, remains one of the most tantalizing mysteries in the history of SETI. Despite decades of follow-up observations, the signal has never been detected again. Numerous explanations have been proposed, including the possibility that it originated from a hydrogen cloud, a comet, or even terrestrial interference, but none have been confirmed. To this day, the WOW signal's origin is officially unexplained. NASA entered the search formally in the 1970s with Project Cyclops, a study examining how to detect extraterrestrial signals. But the political climate turned hostile. In 1981, Senator William Proxmire, who was known for ridiculing what he considered wasteful government spending, gave his infamous Golden Fleece Award to NASA's SETI program and helped defund it. The search went underground, surviving on shoestring budgets and the passion of dedicated scientists. It was not until 1995 that the SETI Institute launched Project Phoenix, which became the most sensitive and comprehensive search for extraterrestrial intelligence up to that point, running until 2015. Project Phoenix targeted roughly 800 nearby Sun-like stars using some of the world's largest radio telescopes. It found nothing. Then, in 2015, something transformative happened. Russian-Israeli billionaire Yuri Milner, a physics graduate who had been inspired by the search for alien life since childhood, announced Breakthrough Listen, a $100 million 10-year program that would be the most ambitious SETI project in history. Breakthrough Listen would survey the 1 million nearest stars, the entire galactic plane of the Milky Way, and the 100 nearest galaxies, using the Green Bank Telescope in West Virginia, the Parkes Telescope in Australia, and other facilities. The project would generate more data in a single day than previous SETI programs had collected in their entire histories. It was a quantum leap in capability. As of the most recent reports, Breakthrough Listen has surveyed enormous swaths of the sky with unprecedented sensitivity. The results are consistent with everything that came before. No confirmed detection of extraterrestrial intelligence. The universe remains silent. And it is not just that we have been listening. We have also been shouting. Humanity has not merely searched for signals from other civilizations. We have actively sent our own messages into the cosmos, announcing our presence to anyone or anything that might be listening. This is a crucial part of the story because the dark forest theory has very specific and very disturbing things to say about what happens to civilizations that announce themselves. Our first deliberate physical messages were the pioneer plaques. In 1972 and 1973, NASA launched Pioneer 10 and Pioneer 11, robotic spacecraft designed to study Jupiter and Saturn before continuing on trajectories that would carry them out of our solar system entirely. Carl Sagan and Frank Drake designed gold anodized aluminum plaques to be attached to each spacecraft, carrying a message intended for any extraterrestrial civilization that might someday encounter them. The plaques depicted nude figures of a human male and female, drawn to scale next to a silhouette of the spacecraft itself. They included a diagram of our solar system, showing the spacecraft's trajectory from the third planet. They showed the position of the Sun relative to 14 pulsars, rapidly rotating neutron stars that emit regular pulses of radio waves, each with a distinctive frequency. These pulsars served as a kind of cosmic address, a way to pinpoint our Sun's location in the galaxy, and they included a representation of the hydrogen atom in its two lowest energy states, providing a universal unit of measurement. These plaques are now heading out of our solar system on trajectories that will carry them past other stars over the course of hundreds of thousands of years. They are among the most distant human-made objects in existence. 5 years later, in 1977, humanity sent an even more elaborate message. The Voyager Golden Records were two identical gold-plated copper phonograph records, one aboard Voyager 1 and the other aboard Voyager 2. A committee chaired by Carl Sagan selected the contents, which were astonishing in their ambition. Each record contained 115 images encoded in analog form, depicting life and civilization on Earth, everything from the structure of DNA to photographs of humans, cities, animals, and landscapes. The records carried natural sounds: thunder, wind, surf, birdsong, whale calls, and the cries of a human infant. There were spoken greetings in 55 different languages, from ancient Sumerian to modern English. There were 90 minutes of music, ranging from Beethoven's Fifth Symphony, to Chuck Berry's Johnny B. Good, to Javanese gamelan, to a Navajo night chant, and there was a message from then-President Jimmy Carter. This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. Each record came with a cartridge and a needle, along with symbolic instructions for how to play it, using the same pulsar map from the Pioneer plaques to indicate our location. Voyager 1 is now in interstellar space, more than 15 billion miles from Earth, moving at about 38,000 miles per hour. It is the farthest human-made object from our planet, and it carries with it a message from our species to anyone who might find it drifting in the dark between the stars. And then there was the Arecibo message. On November 16, 1974, during a ceremony marking the completion of a major upgrade to the Arecibo Observatory's radio telescope in Puerto Rico, astronomers beamed a carefully crafted radio message toward the globular star cluster M13, a dense collection of roughly 300,000 stars located about 25,000 light-years away in the constellation Hercules. The message was written by Frank Drake, with help from Carl Sagan and others. It was 1,679 bits long, a number chosen because it is the product of two prime numbers, 23 and 73. This meant that when arranged in a grid of 23 columns and 73 rows, the bits formed a picture, a simple image containing encoded information about humanity. The message included our counting system in binary, the atomic numbers of the elements that make up DNA, hydrogen, carbon, nitrogen, oxygen, phosphorus, the chemical formulas for the nucleotides that compose DNA, a graphic representation of the DNA double helix, a stick figure of a human being with its approximate height, the population of Earth at the time, roughly 4 billion, a diagram of our solar system with Earth highlighted, and a representation of the Arecibo telescope itself, along with its diameter. The message traveled at the speed of light. It will take 25,000 years to reach M13. Even if someone there receives it and immediately responds, we will not hear the reply for another 25,000 years. The Arecibo message was partly symbolic, a demonstration of human technological capability, but it was also a real signal, a deliberate beacon projected into the cosmos. There have been other deliberate messages since then. The cosmic call transmissions were sent from the Evpatoria radar telescope in Ukraine in 1999 and 2003, targeted at several nearby sun-like stars. The Teenage Message, organized by Russian scientists and composed largely by teenagers, was transmitted in 2001. A message from Earth was beamed toward Gliese 581c, a potentially habitable exoplanet, in 2008. Each of these represented humanity choosing to announce itself to the universe. But all of these deliberate messages are dwarfed by the signals we have been leaking accidentally. Since the early 20th century, Earth has been radiating electromagnetic emissions into space, the byproduct of our radio broadcasts, television signals, radar installations, and telecommunications infrastructure. These signals travel outward at the speed of light, forming an expanding bubble of detectable electromagnetic radiation centered on Earth. That bubble is now roughly 100 to 200 light-years in radius, encompassing thousands of star systems. Within that bubble, a civilization with a sufficiently sensitive radio telescope could, in theory, detect our presence. Our earliest radio transmissions, dating from the 1920s, are now over 100 light-years away. Our television broadcasts from the 1950s are over 70 light-years away. Our most powerful military radar signals are detectable at even greater distances. We have been announcing our existence for over a century, and there is no way to call those signals back. Now, it is important to add nuance here. Our signals weaken dramatically with distance, following the inverse square law. A casual television broadcast from Earth would be extraordinarily faint by the time it reached even the nearest star systems. The most sensitive radio telescopes on Earth, as of the late 2010s, could not detect non-directional radio signals from a civilization like ours, even at a fraction of a light year. So casual leakage may not be detectable at interstellar distances. But powerful, focused signals like military radar, the Arecibo message, or other deliberate transmissions could be detectable much farther away, especially by a civilization with technology more advanced than ours. And remember, the context here is the Milky Way galaxy, which is 100,000 light-years across. Our 200 light-year radio bubble is less than 0.2% of the galaxy's diameter. It is a tiny, faint whisper, but it is a whisper nonetheless. And in the dark forest, even a whisper can be fatal. This brings us to the METI controversy, which is one of the most heated debates in modern science, and which directly connects to the dark forest theory. METI stands for Messaging Extraterrestrial Intelligence, as opposed to SETI, which stands for Search for Extraterrestrial Intelligence. SETI is passive. We listen. METI is active. We transmit. And a significant number of scientists believe that METI is profoundly dangerous. In 2015, a group of prominent scientists, science fiction writers, and intellectuals signed a statement that read in part, We know nothing of ETI's intentions and capabilities, and it is impossible to predict whether ETI will be benign or hostile. The signatories argued that before humanity sends any more deliberate messages into space, there should be a worldwide discussion about the risks. They believed that the decision to contact an alien civilization was not one that any individual, organization, or even nation had the right to make unilaterally, because the consequences would affect the entire human species. Stephen Hawking, one of the most celebrated physicists of the modern era, was among the most vocal critics of METI. In 2010, he made his position strikingly clear. He said that if aliens ever visited Earth, the result might be similar to what happened when Christopher Columbus landed in the Americas, which, as Hawking noted, did not turn out very well for the Native Americans. Hawking speculated that advanced alien civilizations might be nomads, drifting through space in massive ships, having exhausted the resources of their home planets, looking to conquer and colonize whatever planets they could reach. He believed that the risk of contact with such civilizations was so great that humanity should avoid drawing attention to itself. On the other side of the debate, Douglas Vakosh, the president of METI International, argued that the fear was overblown. His reasoning was that if hostile aliens with the technology to reach us existed, they could almost certainly already detect us. Earth's biosignatures, the oxygen in our atmosphere, the presence of water, the telltale signs of an inhabited planet, have been visible across interstellar distances for billions of years. Our radio emissions, while relatively recent, are not the only evidence of our existence. If someone is looking, they already know we are here. Trying to hide, Vakosh argued, is like closing your eyes and hoping the predator cannot see you. It does not work if the predator has already spotted you. This debate is more than academic, it is existential, and it leads directly to the central question of this video. Is the universe a place where contact would lead to friendship, exchange, and mutual enrichment? Or is it a place where contact leads to annihilation? To answer that question, we need to examine the proposed solutions to the Fermi Paradox, all of which try to explain the Great Silence. And then we need to understand why one particular solution stands out as perhaps the most logically airtight and the most terrifying of them all. Scientists have proposed dozens of solutions to the Fermi Paradox over the decades, and they broadly fall into three categories. The first category says that alien civilizations simply do not exist, that we are alone or nearly alone in the universe. The second says that they exist but we cannot detect them for various reasons. The third says that they existed at some point, but are now gone. Let us walk through the most important of these before we reach the dark forest. The first major solution in the first category is the rare Earth hypothesis, proposed by geologist Peter Ward and astronomer Donald Brownlee in their 2000 book of the same name. Their argument is that, while simple microbial life might be relatively common in the universe, complex multicellular life, and especially intelligent technological life, is extraordinarily rare. Earth, they argue, is the beneficiary of an almost impossibly unlikely combination of conditions. We orbit a stable, middle-aged star of the right type. We are at precisely the right distance from that star for liquid water to exist on our surface. We have a large moon, formed by a freak collision 4.5 billion years ago, whose gravitational influence stabilizes the tilt of Earth's axis, preventing wild climate swings that would make complex life impossible. We have a magnetic field generated by a molten iron core, which shields our atmosphere from the solar wind that would otherwise strip it away. We are in a relatively quiet region of the galaxy, far from the supernova explosions and gamma-ray bursts that occur more frequently near the galactic center. We have Jupiter, a massive gas giant whose gravity acts as a cosmic vacuum cleaner, deflecting asteroids and comets that would otherwise bombard the inner solar system and cause frequent mass extinctions. We have plate tectonics, a geological process that recycles carbon and regulates our planet's temperature over billions of years. Each of these conditions is necessary for complex life. The probability of all of them existing simultaneously on a single planet may be vanishingly small. If the rare Earth hypothesis is correct, we may be not just rare but unique, the only complex, intelligent, technological civilization in the galaxy, or even in the observable universe. The second major solution in this category is the Great Filter, a concept introduced by economist Robin Hanson in 1996. Hanson's insight was deceptively simple. Between dead matter and an advanced spacefaring civilization, there are many steps. The formation of a habitable planet, the origin of life, the development of complex cells, the evolution of multicellular organisms, the emergence of intelligence, the development of technology, and the expansion into space. Somewhere in that sequence, there must be at least one step that is almost impossibly difficult, a step so unlikely that virtually no civilization ever passes through it. Hansen called this the Great Filter. The critical question, the one that determines whether the Great Filter is good news or bad news for humanity, is where the filter lies. If the Great Filter is behind us, if it is one of the early steps like the origin of life or the development of complex cells, then we have already passed through the hardest part. We are special because we survived what almost no one else could. This is the optimistic scenario. The universe is silent because life rarely gets started or rarely becomes complex, but once it does, it tends to survive and flourish. But if the Great Filter is ahead of us, then something in our future, some challenge we have not yet faced, is the thing that destroys virtually every civilization before it can become spacefaring. This is the terrifying scenario. It could be nuclear war, it could be climate collapse, it could be artificial intelligence that turns against its creators. It could be a technology we have not yet invented that proves inevitably self-destructive. It could be something we cannot even imagine. If the Great Filter is ahead of us, then every civilization in the galaxy has reached roughly our level of development and then destroyed itself, and we are next. The evidence is maddeningly ambiguous. Life on Earth appeared relatively quickly after the planet formed, within the first billion years, which might suggest that the origin of life is not particularly difficult. But we have exactly one example. We cannot tell from a single data point whether the origin of life was easy or an astronomically unlikely fluke. The development of eukaryotic cells, the complex cells with nuclei that all multicellular life is built from, took roughly 2 billion years, which might suggest that this step is particularly difficult. The jump from single-celled to multicellular life took another billion years. The development of intelligence happened relatively late in Earth's history. Each of these steps could be the Great Filter, or the filter could be something else entirely. Moving to the second category, the solutions that say alien civilizations exist but we cannot see them, the most famous is the zoo hypothesis, proposed by astronomer John Ball in 1973. Ball suggested that advanced extraterrestrial civilizations might be aware of us, but deliberately avoiding contact, like zookeepers observing animals without interfering with their natural behavior. Perhaps there is a cosmic ethic of non-interference, a galactic prime directive, as Star Trek imagined it. The appeal of this idea is obvious. It explains both the existence of aliens and their silence. But it has a critical weakness. For the zoo hypothesis to work, every single advanced civilization in the galaxy must agree to leave us alone. Everyone, if even a single civilization or even a single individual within a civilization decided to make contact, the hypothesis breaks down. A cosmic consensus of non-interference is extremely implausible. Another solution in this category is the communication mismatch. Perhaps aliens are communicating all the time, but using methods we cannot detect: neutrino beams, gravitational waves, quantum-level phenomena, or technologies so far beyond our current understanding that we cannot even conceive of them. We have been searching primarily in radio and optical wavelengths. What if we are scanning the wrong part of the spectrum entirely? This is a real possibility, but it does not fully resolve the paradox. Because a civilization that had been communicating for millions of years would likely have tried many methods, including radio, at some point in their history. Their old, primitive signals should still be detectable, washing across the galaxy like echoes. There is also the simple distance and time problem. The universe is vast beyond comprehension. Even at the speed of light, it takes 4 years to reach the nearest star system, Alpha Centauri. The nearest sun-like star with a known planet is about 12 light-years away. The Milky Way is 100,000 light-years across. Even if civilizations exist, they may be so far apart that no one has had time to reach anyone else. Communication at light speed means a conversation with a civilization 1,000 light-years away would take 2,000 years for a single exchange. Meaningful dialogue over such distances is essentially impossible on human timescales. In the third category, solutions that suggest alien civilizations existed but are now gone. The most prominent is the self-destruction hypothesis. This is the idea that every civilization that develops advanced technology eventually destroys itself. The reasoning is grimly plausible. On Earth, we developed nuclear weapons in 1945, and within 2 decades had assembled arsenals capable of destroying civilization multiple times over. We came within minutes of nuclear war during the Cuban Missile Crisis in October 1962. We narrowly avoided catastrophe during the Able Archer 83 NATO exercise, when Soviet early warning systems misidentified the exercise as a real nuclear first strike. We have experienced multiple false alarms, where the decision of a single individual, sometimes a single military officer, was all that stood between us and annihilation. And nuclear weapons are just one existential threat. Climate change, engineered pandemics, artificial superintelligence, technologies we have not yet invented, all of these could potentially destroy us. If this pattern is universal, if every civilization that reaches our level of technology eventually destroys itself, then the universe is littered with the ruins of dead civilizations, and the silence is the silence of a graveyard. There is also the resource exhaustion hypothesis. Civilizations inevitably consume their home planet's resources before developing the capability to leave it. They burn through their fossil fuels, their minerals, their atmosphere, and collapse before they can become spacefaring. Earth may be on this trajectory. All of these solutions have some merit. Some are optimistic, some pessimistic, some verifiable, some untestable. But none of them, proponents of the dark forest theory argue, are as logically complete, as self-consistent, or as terrifyingly elegant as the explanation that a Chinese science fiction author put into words in 2008. Liu Cixin was born in 1963 in Yangquan, a city in China's Shanxi province. By profession, he was an engineer at a power plant. By passion, he was a writer of science fiction. His remembrance of Earth's Past trilogy, commonly known in the West as the Three-Body Problem trilogy after its first volume, is widely considered one of the greatest science fiction works of the 21st century. The first book, The Three-Body Problem, published in Chinese in 2006, and translated into English by Ken Liu in 2014, won the Hugo Award for Best Novel in 2015, becoming the first novel, originally written in a language other than English, to win that award. The trilogy was adapted into a major Netflix series in 2024, but it is the second book, The Dark Forest, published in 2008, that contains the idea we are here to discuss. In The Dark Forest, a character named Ye Wenjie introduces the foundations of a new discipline she calls cosmic sociology, the study of the relationships between extraterrestrial civilizations. She does this while visiting her daughter's grave, a setting that gives the scene an additional layer of emotional weight. Ye Wenjie establishes 2 axioms, the foundational assumptions upon which all of cosmic sociology is built. And from these axioms, combined with 2 additional logical concepts, the dark forest theory emerges with a kind of mathematical inevitability. It is essential to understand that while the dark forest theory originated in fiction, the logic behind it is drawn from real scientific and mathematical principles, specifically game theory, evolutionary biology, and the physics of interstellar communication. The theory has been analysed in academic papers published in the Journal of the British Interplanetary Society and has been the subject of formal study at institutions including Stanford University. Liu himself has stated that the dark forest is not based on any specific existing scientific theory, but rather on his own logical construction. However, the logic has proven robust enough to be taken seriously as a legitimate hypothesis in the scientific debate over the Fermi Paradox. Let us now walk through the dark forest theory step by step. No shortcuts, no simplifications. Every axiom, every concept, every logical step, laid out in full. The first axiom is this: survival is the primary need of a civilization. This may seem obvious, but it is worth examining carefully, because it is the bedrock upon which everything else is built. Every civilization, regardless of its biology, its culture, its philosophy, or its technology, must prioritize its own survival. This is not a choice. It is a consequence of natural selection. Any civilization that does not prioritize survival will, by definition, cease to exist. The civilizations that remain in the universe are precisely those that treat survival as their most fundamental imperative. because all the others have been eliminated by their own negligence, by natural catastrophe, or by other civilizations. This is not a statement about what civilizations should do. It is a statement about what surviving civilizations inevitably do. It is a tautology. Survivors are those who survived. On Earth, this principle is universal across all life. Organisms that do not effectively pursue survival, that do not feed, reproduce, and avoid threats, are selected against. They disappear. The organisms that remain are those that are good at surviving. The same logic applies at the civilizational scale. Over cosmic time, the only civilizations that still exist are those that treated survival as paramount. Whatever their initial values, whatever their original philosophies, the selective pressure of the universe ensures that the surviving population of civilizations is dominated by those that prioritize self-preservation. The second axiom is this: civilization continuously grows and expands, but the total matter in the universe remains constant. This is again grounded in observable reality. Life expands. It fills available niches. On Earth, life has colonized every environment, from the deepest ocean trenches to the upper atmosphere, from boiling hot springs to the ice sheets of Antarctica. Bacteria have been found living in solid rock miles beneath the surface. Given the opportunity, life spreads. Civilizations do the same. Human civilization has expanded from its origins in Africa to every continent, from the ocean floor to low Earth orbit. We are already planning missions to Mars. The drive to expand appears to be a fundamental characteristic of life itself. But the universe, while vast, is finite. The total amount of matter, the stars, the planets, the gas clouds, the asteroids, the dust, does not increase. It is a fixed quantity. This means that as civilizations expand, they will eventually encounter the limits of available resources. Not today, not tomorrow, perhaps not for millions or billions of years, but eventually, on cosmic timescales, resources become a constraint. And when resources are finite and the number of civilizations competing for them grows, conflict becomes possible. Not inevitable in any single encounter, but possible enough that it must be accounted for in any rational survival strategy. Now, these two axioms alone are not sufficient to derive the dark forest theory. After all, on Earth, nations with competing survival needs and finite resources have found ways to coexist, at least partially. International trade, diplomacy, treaties, and institutions like the United Nations have enabled a degree of cooperation, even between rivals. If civilizations on a single planet can manage this, why could civilizations across the stars not do the same? This is where the two additional concepts come in, and they are what make the dark forest theory uniquely terrifying. They are the chain of suspicion and the technological explosion. The chain of suspicion is the intellectual heart of the dark forest theory, and it is worth taking the time to understand it deeply, because it is what transforms a simple survival calculation into an inescapable logical trap. Imagine that Civilization A discovers Civilization B across the stars. Perhaps A detects B's radio emissions, or observes the atmospheric signature of an inhabited planet, or discovers an artifact in space, and now knows that B exists. The first question A must ask is, what are B's intentions? Is B benevolent, a civilization that seeks peace, cooperation, and mutual benefit? Or is B malevolent, a civilization that will attack and destroy any rival it encounters? Let us say, for the sake of argument, that B is benevolent. A has nothing to fear, but here is the problem. A has no way to verify this. A cannot read B's mind. I cannot examine B's culture, history, or values with any reliability. B is an alien civilization, separated from A by light years of space, with entirely different biology, psychology, and cultural development. It has no frame of reference for understanding B's intentions. B might claim to be benevolent, but A has no way to know if B is telling the truth. But let us go further. Let us say that through some extraordinary means, A does manage to determine that B is genuinely benevolent. A can now relax. Right. Wrong. Because now A must ask a second question. Does B think A is benevolent? Even if B is peaceful, if B believes that A might be hostile, then B might attack A preemptively out of self-defense. So A's safety depends not just on B's actual intentions, but on B's assessment of A's intentions. But it does not stop there. Even if A somehow knows that B thinks A is benevolent, A must now ask, does B know that A knows that B thinks A is benevolent? Because if B is uncertain about A's knowledge of B's assessment, B might still act defensively. And then, does A know that B knows that A knows? And does B know that A knows that B knows that A knows? This creates an infinite regression, an endless chain of mutual uncertainty that can never be resolved. Each link in the chain introduces another layer of doubt, another reason for fear, another justification for preemptive action. And the chain cannot be broken. Why can it not be broken? On Earth, chains of suspicion between nations are broken through communication. Fast, iterative, verifiable communication. Diplomats meet face to face. Hotlines are established. Treaties are signed and verified through inspections. Cultural exchanges build mutual understanding. The speed of communication on Earth is effectively instantaneous for diplomatic purposes, even using technologies as simple as the telephone. And, critically, all parties on Earth are members of the same species. We share biology, emotions, facial expressions, body language, and cultural touchpoints that enable us to interpret each other's intentions with at least some degree of accuracy. None of these conditions hold across interstellar distances. Communication between two civilizations separated by 100 light-years would take 100 years for a message to travel in one direction. A single round trip, one message sent and one reply received, would take 200 years. Building the kind of trust that requires dozens of exchanges, clarifications, verified actions, and cultural familiarity would take thousands or tens of thousands of years. And during all of that time, anything could change. One civilization could undergo a revolution. A new government might repudiate the agreements of its predecessors. A technological breakthrough might shift the balance of power. The civilization you were negotiating with 10 generations ago might be completely unrecognizable by the time your latest message arrives. And even if communication were faster, the fundamental problem remains. The two civilizations are alien to each other in the deepest sense of the word. They do not share biology. They do not share evolutionary history. They do not share psychology. The concepts of honesty, trust, goodwill, and cooperation may not even exist in the other civilization's conceptual framework. Or they may exist but in forms so different from ours that any attempt at mutual understanding is doomed to produce dangerous misinterpretations. On Earth, even between human cultures that share the same species and the same planet, misunderstandings have led to wars. Between genuinely alien civilizations, separated by light years, the possibilities for miscommunication are almost infinite. The chain of suspicion, therefore, leads to a devastating conclusion. When encountering another civilization across interstellar distances, you can never truly know their intentions, and they can never truly know yours. And you can never verify that they know that you know, or that they know that you know that they know. The chain extends infinitely, and at every link, the rational response to uncertainty is suspicion. And the rational response to suspicion, when the stakes are the survival of your entire species, is fear. But perhaps you might think, this fear is manageable. Even if you cannot trust the other civilization, you could still decide that the risk of contact is worth the potential reward. Perhaps you are confident in your own strength. Perhaps you are so technologically advanced that no other civilization could threaten you. This is where the second concept comes in, and it closes the trap. The technological explosion refers to the observed phenomenon that technological progress does not proceed at a steady, predictable rate. It is exponential, and it can happen in shockingly brief bursts. Consider Earth's own history. In 1900, the most advanced vehicles were horse-drawn carriages and steam-powered trains. The first powered airplane flight did not occur until 1903. 66 years later, in 1969, humans walked on the moon. In the span of a single human lifetime, we went from the horse and buggy to leaving footprints on another world. The first electronic computer, ENIAC, was built in 1945. It weighed 30 tons, filled an entire room, and could perform about 5,000 additions per second. Today, the smartphone in your pocket is millions of times more powerful. This transformation happened in about 80 years. In 1945, the most powerful weapon was the gun. Then, in a single year, we split the atom and built a device that could destroy an entire city in seconds. The progression from the first fission bomb to the hydrogen bomb, a weapon 1,000 times more powerful, took just 7 years. This pattern of sudden, explosive technological advancement is not unique to humanity. It appears to be a fundamental feature of how technology develops. Once the right conditions are met, the right combination of knowledge, resources, and motivation, technological progress can accelerate at a rate that is almost impossible to predict in advance. A civilization that is in its equivalent to the Stone Age today could, theoretically, undergo a technological explosion in a few centuries, or even a few decades, and emerge as a civilization with capabilities that dwarf anything its neighbors possess. Now, apply this to the interstellar context. Civilization A discovers Civilization B. B appears to be technologically primitive, far less advanced than A. A might feel safe, perhaps even smug. B poses no threat. But here is the problem. A is far away from B. Even at the speed of light, reaching B might take decades or centuries, and during that time, B could undergo a technological explosion. By the time A's fleet arrives at B's planet, B might possess weapons that make A's look like toys. The primitive civilization that are dismissed as harmless could become the most dangerous entity in the galaxy in what, by cosmic standards, is the blink of an eye. This means that technological superiority is never a guarantee of safety. It is temporary. It is fragile. It can be reversed. The only way to ensure that a rival civilization never becomes a threat is to eliminate it before it has the chance to undergo a technological explosion. And since you cannot predict when a technological explosion will occur, the only truly safe strategy is to act immediately. Now, combine all of these elements. Axiom 1, every civilization must survive. Axiom 2, resources are finite and civilizations expand. Concept 1, you can never know another civilization's intentions, and they can never know yours, and this uncertainty is permanent and unresolvable. Concept 2, a civilization that is weak today can become devastatingly powerful tomorrow, in a time frame that is cosmically insignificant. What is the rational strategy? What is the only strategy that guarantees survival? The answer is as simple as it is horrifying. If you discover another civilization, you have exactly one rational option. Destroy it. Immediately, before it can become a threat, before it can undergo a technological explosion, before the chain of suspicion can spiral into a conflict that you might lose. You do not wait. You do not attempt to communicate. You do not try to assess whether they are benevolent or malevolent, because you can never know for certain, and the cost of being wrong is the extinction of your species. And if you cannot destroy them, if they are too far away or too well hidden, then the next best option is to hide. Make yourself invisible. Suppress your electromagnetic emissions. Avoid anything that could reveal your location. Become silent. Because if the universe operates on this logic, then every other civilization in it has arrived at the same conclusion. And they are all watching and listening. And if they find you, they will do exactly what you would do to them. This is the dark forest theory. The universe is a dark forest, and every civilization is an armed hunter stalking through the trees like a ghost, pushing aside branches with infinite care, trying to move without making a sound. Even breathing is done carefully. The hunter must be cautious, because everywhere in the forest, hidden among the trees, are other hunters just like him. If he encounters another presence, another hunter, an angel, a demon, a fragile infant, a tottering elder, it does not matter what they are. There is only one thing he can do: open fire, eliminate them. Because in the dark forest, every other living thing is an existential threat. And this is the answer to the Fermi Paradox. The universe is not empty. It is full of civilizations that have learned, through logic or through bitter experience, the supreme lesson of the dark forest. Silence is survival. The civilizations that spoke up, that broadcast their presence, that reached out in hope and curiosity, are gone. They were found, and they were destroyed. The ones that remain are the ones that understood, perhaps from the very beginning, that the safest thing to do in a forest full of armed hunters is to say nothing at all. In the third book of Liu Cixin's trilogy, Death's End, there is a chapter that illustrates the dark forest at its most mature and most chilling. It features an alien entity known as Singer, a member of a civilization that acts as one of the hunters, or more precisely, one of the cleaners of the dark forest. Singer's job is to destroy star systems that have revealed themselves. He does this casually, almost absent-mindedly, the way a gardener might pull weeds, or a farmer might crush insects. It is not personal, it is not malicious, it is simply maintenance. Singer fires a small projectile, what Liu calls a photoid, a fragment of two-dimensional matter, at the offending star system. When it arrives, it triggers a process called dimensional reduction, collapsing three-dimensional space into two dimensions. Everything in the affected area, stars, planets, moons, civilizations, everything, is flattened into a two-dimensional plane and destroyed utterly and irrevocably. Singer does not think of this as murder. He thinks of it as hygiene. He thinks of it the way we might think of swatting a mosquito. What is remarkable about the Singer chapter is not just the scale of destruction, but the scale of indifference. Singer is not a villain. He does not hate the civilizations he destroys. He barely thinks about them. They are simply noise in the forest, noise that must be silenced to protect the larger order. And Singer's civilization, powerful as it is, lives in fear of the truly dangerous entities in the cosmos. Civilizations even more powerful, even more hidden, even more ruthless. Even the hunters are afraid. This is the Dark Forest taken to its logical conclusion. It is not a universe of villains. It is a universe of survivors. And the price of survival is silence. The Dark Forest theory is not just a philosophical exercise. It can be analyzed rigorously using the tools of game theory, the mathematical study of strategic decision-making. In game theory, the Dark Forest represents what is known as a sequential and incomplete information game, a scenario in which players make decisions in sequence, each with limited knowledge about the other's choices, strategies, and intentions. Consider the situation as a payoff matrix. Two civilizations, A and B, each face a choice: destroy the other or do nothing. If both choose to destroy, both are eliminated, a mutual catastrophe. If A destroys B but B does nothing, A survives and B is annihilated. If B destroys A but A does nothing, B survives and A is annihilated. If neither destroys the other, both survive for now, but each faces ongoing risk, the risk that the other might attack in the future, the risk of a technological explosion shifting the balance of power, the risk that a third civilization might detect both of them as a result of their interaction and destroy them both. In game theory, the Nash equilibrium, the outcome where neither player can improve their position by unilaterally changing their strategy, is the point where both players choose to destroy. This is because the cost of not destroying, when your opponent does, is infinite. The total extinction of your species, against a potential infinity of loss, any finite cost of attacking is rational. Even if the probability of the other civilization being hostile is low, even if it is 1% or 1/10 of 1%, the expected value of not attacking is still catastrophically negative, because the potential loss is unbounded. This parallels the classic prisoner's dilemma, but with infinitely higher stakes. In the prisoner's dilemma, two players can cooperate or defect. The optimal outcome for both is mutual cooperation, but the rational choice for each individual, absent trust, is to defect. In the cosmic version, the defection is preemptive destruction, and the penalty for misplaced trust is not a prison sentence, but the annihilation of your entire civilization. Under these conditions, the rational equilibrium is always mutual destruction, or rather, the first civilization to act destroys the other before the other has a chance to respond. Stanford University's analysis of the Dark Forest formally models this, assuming the axioms of survival and expansion and the constraints of the chain of suspicion and technological explosion. There are only three types of civilizations that can survive in the long term. First, civilizations that have not yet been detected by anyone. Second, civilizations that are extremely good at hiding themselves. Third, civilizations that always destroy any other civilization they discover. All other types, the curious, the friendly, the open, the optimistic, have been eliminated by the logic of the forest. Natural selection, applied at the civilizational scale, produces a universe populated exclusively by the hidden and the lethal. Now, let us ground this theory in the real-world observations and scientific frameworks that make the silence feel so heavy. In 1964, Soviet astronomer Nikolai Kardashev proposed a scale for classifying civilizations based on their total energy consumption. A Type 1 civilization harnesses all the energy available on its home planet, roughly 10 to the power of 16 watts. Earth's civilization is currently at approximately 0.7 on this scale, meaning we do not yet fully harness even our own planet's resources. A Type 2 civilization harnesses the entire energy output of its star, roughly 10 to the power of 26 watts. The theoretical mechanism for this is a Dyson sphere, a hypothetical megastructure that partially or fully encloses a star to capture its energy. A Type 3 civilization harnesses the energy of its entire galaxy, roughly 10 to the power of 36 watts. Under the dark forest theory, a Type 2 or Type 3 civilization would be a hunter of terrifying capability, able to detect and destroy other civilizations across vast distances, with energy resources that make resistance essentially impossible. A Type 1 civilization, or a civilization below that level, like ours, would be an easy target, technologically advanced enough to be detectable, we are leaking radio signals, but far too primitive to defend itself against a civilization that has harnessed the power of a star or a galaxy. In 2015, astronomers announced one of the most puzzling observations in recent astronomy. A star designated KIC 846 2852, quickly nicknamed Tabby's star, after the astronomer Tabitha Boyajian, who led the team that identified its anomalous behavior, was showing bizarre and irregular dimming patterns. The star's brightness was fluctuating in ways that could not be explained by any known natural phenomenon. Some dimming events reduced the star's brightness by up to 22%, an enormous amount, far more than could be caused by any planet passing in front of it. The dimming was also irregular, not periodic, ruling out simple orbital mechanics. The observation triggered immediate speculation. Could this be an alien megastructure? A partially constructed Dyson sphere, the Breakthrough Listen project trained its instruments on Tabby's star, searching for artificial signals. The results were negative. No signs of technological origin were found. Subsequent studies, published in 2018, concluded that the dimming is most likely caused by fine dust orbiting the star, which would block different amounts of light depending on its configuration, producing the observed irregular patterns. The mystery was, if not fully solved, at least given a plausible natural explanation. But the significance of the Tabby's star episode goes beyond the specific case. It demonstrates that scientists are actively looking for the signatures of advanced civilizations, the kind of techno-signatures that a Kardashev Type 2 civilization would produce. Dyson spheres, if they exist, would alter the infrared spectrum of the stars they surround in predictable ways. If any star in our galaxy had been enclosed in such a structure, we would likely be able to detect it, and we have not. Surveys of entire galaxies, searching for excess infrared radiation that would indicate widespread stellar engineering, have found nothing unusual. The universe, as far as we can see, shows no signs of large-scale engineering by any civilization. Either no civilization has reached that level, or those that have are very, very good at hiding what they have built. Another concept that sharpens the Fermi Paradox and connects to the dark forest is the von Neumann probe. In 1948, mathematician John von Neumann theorized self-replicating machines, devices that could build copies of themselves from raw materials. Applied to space exploration, the concept becomes extraordinarily powerful. A civilization could build a single self-replicating probe and launch it toward a nearby star system. Upon arrival, the probe would mine local resources, build copies of itself, and send those copies toward the next star systems. Each copy would do the same. The process would be exponential, like a chain reaction, a single probe becoming 2, becoming 4, becoming 8, and so on. Even traveling at modest speeds, perhaps 10% of the speed of light, such probes could colonize the entire Milky Way galaxy in roughly 1 to 10 million years. On a cosmic timescale, this is practically nothing. The galaxy has existed for over 13 billion years. Even if it took a civilization a billion years to develop von Neumann probes, there would still have been over 12 billion years for those probes to spread. This makes the Fermi Paradox razor sharp. Even one civilization at any point in the galaxy's history, launching von Neumann probes, should have resulted in every star system in the Milky Way being visited by now. And yet, we see no evidence of this. Our solar system shows no signs of alien probes, mining operations, or any other artificial presence. The dark forest theory provides an explanation. No civilization launches von Neumann probes because doing so would be tantamount to painting a target on yourself. The probes would spread your technological signature across the galaxy, announcing your existence and your capabilities to every other civilization. In a dark forest full of armed hunters, scattering breadcrumbs across the forest floor is suicidal. A darker variant of the von Neumann probe concept is the Berserker hypothesis, named after Fred Saberhagen's 1960s science fiction series. What if some civilization, at some point in the galaxy's history, launched self-replicating probes that were not explorers but weapons? Autonomous machines programmed to seek out and destroy any life they encountered, spreading from star to star, replicating endlessly, and cleansing the galaxy of biological civilizations. This is the dark forest theory mechanized, the logic of preemptive destruction automated and made permanent. The astrophysicist David Brin discussed this concept in his 1983 survey of Fermi Paradox solutions, calling them deadly probes. The difference between the Berserker hypothesis and the dark forest theory is that Berserker probes would presumably leave detectable evidence of their activity: destroyed star systems, anomalous radiation patterns, debris fields. The dark forest, by contrast, operates in silence. The kills are clean, the evidence is erased, the forest returns to stillness. And the silence we observe is total. Despite more than 60 years of searching with increasingly sophisticated technology across multiple wavelengths of the electromagnetic spectrum, surveying millions of stars and hundreds of galaxies, humanity has found zero confirmed evidence of extraterrestrial intelligence. Breakthrough. Listen, the most ambitious SETI project in history, with a budget of $100 million and access to some of the world's most powerful telescopes, has produced no confirmed detections. The Great Silence, as scientists call it, is not just an absence of evidence. It is evidence of absence, or at the very least, evidence that whatever is out there is either very rare or very, very quiet. The dark forest theory says it is the latter. The universe is not empty. It is holding its breath. But the dark forest theory, compelling as it is not without its critics. And it would be dishonest to present this theory without also presenting the substantive arguments against it. Science is not about finding a theory that sounds convincing and stopping there. It is about testing every claim against evidence and logic, looking for weaknesses and seeing what survives. So, let us now examine the most serious criticisms of the dark forest theory. The first, and perhaps most intuitive criticism, is that the theory assumes all civilizations would reason the same way. On Earth, we see enormous diversity in how cultures approach conflict, cooperation, risk, and the unknown. Some are aggressive, some are peaceful, some are isolationist, some are expansionist, some are driven by fear, some by curiosity. Muya McTeer, an astrophysicist, author, and folklorist, has pointed out that we do not even see this uniform behavior among cultures on a single planet. Some extraterrestrial intelligences might have members that act in perfect unison, driven by a single collective logic. But others, perhaps most, would have diverse and independently behaving factions, some fearful and some curious, some cautious and some bold. If even one faction within even one civilization decides to reach out, to broadcast its presence, to try to make contact, then the dark forest breaks down. That one signal would light up the forest for everyone to see. The counter-argument from within the dark forest framework is chilling in its elegance. It says, yes, diverse civilizations with varying strategies would exist initially, but over cosmic time, natural selection operates on civilizations just as it operates on organisms. The civilizations that broadcast are found, and they are destroyed. The civilizations that hide survive. Over millions and billions of years, this selective pressure weeds out the bold, the curious, and the friendly. What remains is a universe populated exclusively by the silent and the lethal. The dark forest is not the initial state of the universe. It is the equilibrium state, the condition the universe converges toward over time. Every civilization that tried a different strategy is gone. Only the forest remains. The second criticism is that the distances between stars make preemptive strikes impractical. Seth Shostak, a senior astronomer at the SETI Institute, has argued that the vast distances between star systems make the idea of preemptive attack seem unreasonable. Even at the speed of light, an attack on a civilization 100 light-years away would take 100 years to arrive. During that time, the target could detect the incoming attack, develop defenses, relocate, or even launch a retaliatory strike. The attacker would have to commit resources to an attack whose outcome is uncertain, against a target that will have had decades or centuries to prepare. Under these conditions, is preemptive attack really the rational choice? The counter-argument is that the theory does not assume conventional warfare. A sufficiently advanced civilization would not need to send a fleet across interstellar distances. It could use relativistic projectiles, objects accelerated to a significant fraction of the speed of light, which would arrive with devastating kinetic energy and minimal warning time. It could use directed energy weapons, focused beams of radiation that travel at the speed of light itself. In Liu Cixin's novels, the ultimate weapons are far more exotic, photoids that collapse three-dimensional space into two dimensions, annihilating everything in the affected region instantly and irrevocably. We do not know what weapons a civilization millions of years more advanced than ours might possess. The only thing we can say with confidence is that our inability to imagine them does not mean they do not exist. And if they do exist, then the distances between stars, while large by our standards, are not a meaningful barrier for a civilization with sufficient technology. The third criticism concerns resources. Many scientists have pointed out that the resources of the universe are, for all practical purposes, inexhaustible. There are more stars than could ever be used by any number of civilizations. Asteroid belts contain more minerals than any civilization could consume. Why would civilizations compete for resources when there is more than enough for everyone? This is a reasonable point, but it misunderstands the dark forest theory. The theory does not require that civilizations are currently competing for resources. It requires only that the possibility of future competition exists. If civilizations expand, which the second axiom asserts they will, then they will eventually encounter each other. When they do, the chain of suspicion kicks in. The issue is not resource scarcity in the present. It is the impossibility of trusting another civilization's intentions regarding resources, territory, or anything else over the timescales relevant to cosmic civilizations. A civilization might have no interest in your resources today, but can you guarantee that will still be true in 1,000,000 years? In 1,000,000,000 years, you cannot. And the cost of being wrong is extinction. The fourth criticism is that the dark forest theory is anthropocentric, projecting specifically human fears and behaviors onto alien civilizations that might think in entirely different ways. Moya McTeer has said that the theory relies on anthropocentric assumptions that she does not think are fair. Fear, she argues, is a powerful thing, but so is curiosity. Why should we assume that alien civilizations would be driven primarily by fear rather than by wonder, by the desire to explore, to learn, to connect? This is a compelling point philosophically, but the counterargument is that the axioms of the dark forest are not derived from human psychology specifically. They are derived from universal principles. Any entity produced by evolution, the process by which complex life arises from simpler forms through variation and selection, will tend to prioritize survival, because entities that do not prioritize survival are selected against. This is not a human trait. It is a logical consequence of the process that produces complexity in the first place. Similarly, the tendency to expand is not a human trait, but a property of life itself. And the chain of suspicion is not a product of human paranoia, but of the physical constraints of interstellar communication. The speed of light limits how fast information can travel, and the alien nature of the other party limits how well that information can be interpreted. These constraints are universal. They apply to any civilization regardless of its biology or psychology. The fifth criticism, and perhaps the most immediate one, is this. If the dark forest theory is correct, why has Earth not been destroyed already? We have been broadcasting electromagnetic signals into space for over a century. Our radio bubble extends roughly 100 to 200 light years. Thousands of star systems are within that range. If there are hunters in the forest, and we have been making noise for over 100 years, why are we still here? There are several responses to this within the framework of the theory. First, our radio bubble is tiny. The Milky Way is 100,000 light years across. Our signals have reached less than 0.2% of the galaxy. The vast majority of the galaxy has not heard us yet. If the nearest hunter is 10,000 or 50,000 light-years away, our signals simply have not reached them. Second, our signals may not be detectable. Casual radio and television broadcasts degrade rapidly with distance. A civilization would need extremely sensitive equipment to detect Earth's leakage at interstellar distances, and even then, they might not recognize it as artificial. Third, 100 years is nothing on cosmic timescales. The galaxy is 13.6 billion years old. We have been broadcasting for 1/10,000,000th of that time. Even if a hunter has detected our signals, their response might be traveling towards us right now, at the speed of light, and we simply have not been struck yet. The bullet may already be in flight. Fourth, we may genuinely not be worth the effort yet. A pre-spacefaring civilization confined to a single planet might not register as a significant threat. A hunter might observe us and decide to wait to see if we develop into something worth eliminating, or if we destroy ourselves first, saving them the trouble. The theory does not require that every noise in the forest is immediately answered with a bullet. It only requires that any noise that represents a genuine threat is eventually answered. There is also a counter-argument that operates outside the dark forest framework entirely. Karim Jabari, a researcher at the Institute for Future Studies in Stockholm, Sweden, has proposed what might be called the inverse dark forest argument. He points out that if many civilizations exist, and some of them could destroy us, the fact that we have not been destroyed suggests that advanced civilizations have chosen not to attack. Why? Perhaps because they have arrived at the logical conclusion that their own survival proves the same thing. Other civilizations have chosen not to attack them. This creates a basis for trust, not through communication, but through inference. If I am alive, it means no one has destroyed me. If no one has destroyed me, it means the other civilizations are either benign or deterred, and if they are benign or deterred, then I do not need to attack them preemptively either. Jabari argues that this logic could produce a stable, peaceful equilibrium, the opposite of the dark forest. The silence would be evidence not of fear but of mutual trust, arrived at independently by each civilization through pure logic. Economist Noah Smith has mounted what is perhaps the most systematic critique. He argues that the dark forest hypothesis relies on a crucial technological assumption, that civilizations are naturally hidden from each other and only reveal themselves through deliberate signals or accidental leakage. In reality, Smith argues, any sufficiently advanced detection technology would find civilizations regardless of whether they broadcast. The infrared signatures of their energy consumption, the atmospheric changes caused by their industrial activity, the gravitational effects of their megastructures, all of these would be detectable to a civilization with sufficiently advanced instruments. If you cannot hide, the entire premise of the dark forest collapses. You cannot maintain a forest of hidden hunters if hiding is technologically impossible. This is a strong criticism, but it assumes a level of detection capability that may not be realistic. Infrared surveys of the Milky Way have not revealed any obvious signs of advanced civilizations. This could mean either that such civilizations do not exist, or that they have found ways to conceal their presence, perhaps by radiating waste heat in directions away from potential observers, or by using energy sources that do not produce detectable signatures, or by operating on scales or in modes that our current technology cannot identify. We simply do not know. The debate continues. The dark forest theory has not been proven. It has not been disproven. It remains a hypothesis, a proposed explanation for an observed phenomenon, the Great Silence, that is logically consistent with the known facts and the laws of physics. It may be correct, it may be wrong, but it is, without question, one of the most carefully reasoned and deeply unsettling ideas in the history of human thought about our place in the cosmos. Let us now consider the implications. If the dark forest theory is correct, what does that mean for humanity? What does it mean for our past, our present, and our future? The first and most immediate implication is this: humanity has already revealed itself. We did not know about the dark forest when we began broadcasting radio signals in the early 20th century. We did not know about it when Frank Drake aimed his telescope at Tau Ceti and Epsilon Eridani in 1960. We did not know about it when Carl Sagan designed the Pioneer plaques and the Voyager Golden Records. We did not know about it when the Arecibo message was beamed toward M13 in 1974. We did not know about it when the cosmic call and a message from Earth transmissions were sent in the 1990s and 2000s. Every one of those acts, performed in a spirit of hope, curiosity and goodwill, may have been, under the Dark Forest framework, acts of extraordinary danger.